So to go along with using exponential functions is there are common and natural logarithms, and we need to look at them again. Couple reminders about logarithms. We have two different logarithms that we're used to.
Please be quiet. Thank you.
First of all, we dealt with common logarithms, and if you remember, logarithms are inverses of exponential functions. So when we're looking at the exponential function, y equals 10 raised to the power of x. If we wanted to do the inverse of that, we would switch x and y. Well, when we switch x and y, we get x equals 10 raised to the power of y. And with x equals 10 raised to the power of y, we don't have a way of solving for y there. And so that's where we ended up with logarithms. And so when we have a logarithm with a base 10, we call it the common logarithm. And for exponential functions, they all have a domain of all real numbers and a range where y is greater than 0. So our logarithmic functions are going to be just the inverse of that. The domain then has got to be greater than 0, and the range is going to be all real numbers. And that's very important that you remember that, so that you know that if I try to take the logarithm, common or natural, when we start working with them, of a negative number, it can't happen. You get a non-real answer. For the same reason that if you raise 10 to a power, positive or negative, you're always going to get a positive answer. It'll never be negative. So the first thing is just a little reminder about writing between logarithm and exponential functions, but also finding the answers for logarithmic problems. And when we're trying to find an answer for a logarithm, we are actually looking for an exponent. So for instance, if you look at these here, if I have a logarithmic statement that says the log of v equals u, well, that means then is the same, that's equivalent to the exponential statement, 10 to the u is equal to v. So it looks like these. Y equals some number raised to a power, then x is equal to the log base b of y. So y equals b to the power of x. When I find the inverse of it and write it in logarithmic form, it's x equals the log base b of y. So the log of 29, it equals approximately 1.4624. That would be saying the same as 10 to the power of 1.4624 is approximately 29. Log of 378 is approximately 2.5775 because 10 raised to the power of 2.5775 is 378. So it says, without using the calculator, find each value. So basically, what we're finding here then is we want to know ten raised to what power is equal to 100,000. So when we're asking you to simplify the log of 100,000, if there's no number here, then the base is 10, and it's called the common logarithm. So 10 to what power is 100,000? To the fifth. So this is equal to 5. The log of 10. So 10 raised to what power is equal to 10? 1. Okay. Cube root of 10. Okay. Who said 1/3? Gallery, how'd you get that? So you remembered it from Algebra C. What did you remember from Algebra C? Very good. This is the same as the log base 10, or the log of 10 raised to the 1/3 power. All right? That whatever the index is here, okay, that's the denominator for the fraction, and whatever the exponent is there is the numerator for the fraction. Okay? Good job. Now, here's one of the things that happens. Whenever these two things here are the same, okay, then they're inverses of each other. Okay? And so because they're inverses of each other, it just equals that exponent, which is 1/3. Okay? And we could also think of it like we did at the beginning. We could say, okay, 10 to what power is equal to 10 to the 1/3 power? Hopefully 1/3. Okay? And how about letter D? Okay, it's a non-real answer. Because we cannot take the logarithm of a negative number. It's not in the domain. Okay. So log base 10 is a common logarithm. And if the base is 10, there will not be any number here. We're going to focus totally today on base 10 and the natural logarithms, which are base e. And then later on, we'll look at, I think actually on Monday, then we're going to look at the ones that have a different base. All right, the one thing nice about our calculator is it has logarithms on it. That we have right next to the 7 key, we have the key for the common logarithm, the log. And we can use that key sometimes to solve problems. And we will. All right. Now they want us to solve each of these by using the equivalent statement. So this equivalent statement for letter A would be the fact that the base here is 10, right? So 10 to the 5th power is equal to x. Because the base is here, so the base raised to that power is equal to this number here. All right? So that would be back to our friend Mr. 100,000, because there's 5 zeros. And then to find letter B then, solving the equivalent equation then would be the fact that we want to find the log of 52 is equal to x. Okay? Because the base is here, so the log base 10 of 52 is equal to x. That's going back to Algebra C again, okay, where we learned how to write exponential and logarithmic expressions. So that this stuff here, all right, is converting from exponential to logarithmic. If I have y equals b to the power of x, that's the same as x equals the log base b of y. So then for letter B then, I could just take my calculator, type in the log of 52, and we will get 1.716 approximately. Okay. Natural logarithms. Natural logarithms are base logarithms with a base of e. So we have what's called the natural exponent, or the natural base is what e is called, and it's used for mostly compounding things continuously. Right? So we did number 4 yesterday, right, on your example sheet. Okay. And when you did that one, On number 4, you got the number 2.71828, correct? Okay. Should have been close to that number, or 271.828. Is that right? Okay. Now, the natural base e is equal to, so e to the first power is equal to 2.71828. That's the natural base. And that's used for compounding interest continuously. Thanks, Emily. So with the natural base e, if we had y equals e to the power of x, if I write it in logarithmic form, it's the log base e of x, but we use the natural log, so it would be the natural log of x. So when you see ln of x, that's a natural log, and the base there is going to be e. It's called the natural logarithmic function. But still, for the domain and range for the natural logarithm are the same as for the common logarithm. The domain is the number values greater than 0, so x is greater than 0, and the range is all real numbers. And we work with things just like we did with the natural logarithm. So here they're asking us to use our calculator to find these. So we can take our calculator, the ln key, which is the one right below the log key. So take the natural log of 1.3, and we get 0.262. Natural log of 203, 5.313. The natural log of negative 12. All right, it's a non-real answer because you can't take the natural log of a negative number because the domain does not exist in the negatives. The domain is all real numbers greater than 0. So for number 4 here, we try to solve these by using the equivalent statement. For letter A, that means we want to solve the equation e raised to the power of 2 is equal to x. Now, using my calculator then, I will do second natural log to the second power. So approximately 7.389. For letter B then, natural log of 8 is equal to x. Change it to the other form. We took letter A, changed it from logarithmic to exponential. Letter B from exponential to logarithmic. Since the base is e, we're using the natural logarithm. Okay, so hopefully this is just a good reminder. Okay. of wonderful things from the past. Right, Morgan? Okay, the graphs of them. So we're going to look at transformations. Our two basic functions. In exponential forms, 10 to the x and e to the x. Logarithmic, log of x, natural log of x. The domain for exponential, all real numbers. For logarithms, all real numbers greater than 0, or all positive real numbers. Range for exponential, all positive real numbers. Logarithms, all real numbers. Okay. Exponential, f of x increases as x increases. Logarithmic does the same thing. F of x approaches the x-axis as x decreases. So as I'm going to the left, okay, it's getting closer and closer to the x-axis. Okay. So as I move here, as x decreases, I'm going farther and farther to the left. I'm getting closer and closer to 0 with the exponential. With a logarithm, as I get closer and closer to 0 here, it's going to negative infinity. Okay. All right. And there's some specific reference points that you can use too for graphing. Okay, and we're going to look at transformations. So transformations. G of x equals c times f of a times the quantity x minus b plus d. So, reminder of what those are. The letter A is a horizontal stretch or compression. That happens first. The letter B is a horizontal shift to the left if B is negative, to the right if B is positive. C is our vertical stretch or compression. If the absolute value is greater than 1, then it stretches it. If it's between 0 and 1, compresses it. And D is our vertical shift. Moves it up or down, whether it's positive or negative. One thing to remember, the stuff that's inside the parentheses. So these two things here, f of a times quantity x minus b, those are horizontal. So those things always work the inverse. Okay? So if it says x minus 3, it's a movement to the right. If it says 4 times the quantity of that, that means it's going to be a compression by 1/4, not a stretch by 4. Inside is horizontal. Outside is vertical. Do what it says. Okay? So horizontal is the inverse. Vertical things are exactly the same. So number 5 here says describe the transformation from the graph of g of x equals the log of x to the graph of h of x equals 3 log of x plus 4. Give the domain and range of the function. Now, first thing I'm going to do then is I'm going to identify the letters that we're using. The 3 goes along with which letter? It says 3 log of x plus 4. The 3 refers to which letter? A, B, C, or D? C. Okay. The x plus 4, what number am I actually using there? Negative 4, and refers to which number? Or which letter? B. Okay? So C is always our vertical. Here's C, D, C is a vertical stretch or compression. So in this case then it says describe the transformation. So h of x is stretched. That's a C. Stretched vertically by a factor of 3. And shifted 4 units to the left. If the value of C is greater than 1, okay, it's a stretch. If it's between 0 and 1, it's a compression. Okay. So if absolute value of C is greater than 1, it's a stretch. If it's between 0 and 1, it's a compression. And it's just the opposite when we're talking about B. If the absolute value of B is greater than 1, it's compressed. If absolute value of B is between 0 and 1, it's a stretch. Because it's actually the reciprocal then. Okay? So if the value of B, not B, that's A, I'm sorry. It should be A. Okay? If the value of A, you'll notice that it says absolute value of 1 over A. Okay? It's actually the reciprocal. So if we had a value of A of 3, then it would be compressed by 1/3. If I had a value of A of 1/2, it would be stretched by a factor of 2. Okay? Because the value of A, because it's horizontal, the horizontal things are inverse of the vertical things. So if we're multiplying horizontally, it's actually the inverse of that. Okay? So what happens to the domain and range then? Here's the graph of log of x. The domain, y is greater than 0. The range, all real numbers. If I shift this to the left then, 4 units, so here's negative 4, then the graph's going to look like this, except it's going to grow faster, right? Because it's being multiplied by 3. It's stretched vertically. So does the domain change? Do my x values change? Yes, they have moved to the left, negative 4, right? So now for the domain, x is greater than negative 4. Does the range change? Not at all. Okay, it's still all real numbers. Okay. because I moved horizontally, it changes the domain, but that does not affect the range. All right. Your range will never be affected by a transformation of a logarithmic function. Because of its all real numbers. Only the domain will be affected by it. Okay. So this is one way to approach this. Another way is, all right, so let's look at another one. Another way to approach it would be to list the letters A, B, C, and D, and then find out what those values are. Now, the first thing is, we always want it to look we always want our function to look like this first. So for number 6, the first thing we want to do is we want to change it so it's in that format, which means then it's x minus b. If you look at this one, it has basically b minus x, right? So we want to rewrite it in this form. So the first thing I'm going to do is take this logarithm and rewrite it as the natural logarithm of negative 1, because I'm going to factor out that negative. I want my x to be positive. So what I'm going to do is I'm going to factor out the negative. So it'll be a negative 1 times x plus 4, or x minus 4, excuse me. And then plus 2. We always want it in that form. That if it's a natural logarithm, it'd be c natural log of a times x minus b plus d. We always want them in that form. If they're not in that form exactly, then I need to change it so that it does look exactly like that. So the x is always positive 1, the coefficient of it is. Right? You might have to pull something out then. So if we identify A, B, C, and D to write the transformation, to tell what the transformation is. So what's the value of A in this case then? Negative 1. Okay. B is positive 4. C is, if there's no number in front of it, it's 1, right? Okay. And D is 2. Okay. So let's talk about what they all mean. Right? If A is negative 1, and that affects the x, right? Because it's affecting the x here, that means all of my numbers are going to be flipped over, okay? When I multiply by a negative, that means I have a reflection. So this represents a reflection over the x-axis, or the y-axis, excuse me, the y-axis, because it's a horizontal reflection. There we go. B equals 4. This is a horizontal translation, horizontal shift, 4 units to the right. There's no vertical stretch or compression, and then it's moved or shifted up 2 units. So we take for domain and range then. All All right, so first of all, it's reflected over the y-axis. That means instead of going to the right, it's going to go to the left. Okay? And since it's shifted 4 units to the right, that means then it's not going to start at 0, it's going to start at 4. So this graph, we're going to have an asymptote at 4, and it's going to go this way. Does the vertical shift, the fact that it moved up 2 units, does that affect the range? Does it affect the domain? No. Okay, so our domain is now x is less than 4, and our range is still all real numbers. Okay. Now, take out your calculator and put that original function in your calculator to verify that. That's interesting. Oh. So what's going on? Why is that the case? What? Nope. There's not an asymptote at 4, actually, in this case. Okay, so we have, it's not exactly what we thought it was. All right. So what's the problem here? Why does it stop there? What? Okay. Exactly, Maria. The fact is the fact that this says 4 minus x, right? And as soon as I put a number in there for larger than 4, or 4 or larger, I'm going to end up trying to take the natural log of a 0 or a negative number. So it just stops there. It doesn't actually put an asymptote there. So, oh, that's not quite right, is it? Okay. So the way it should look then is, oops, there we go, is this graph actually comes over to here, and we have a little hole there at the point 4, and so we still have the fact that x is less than 4, but our range then is greater than 0. Okay. All right. Very good. Okay. All right. So it's very important to check them too to see what happens. Okay. All right. Number 7. If you invest money at an interest rate R compounded annually, then T of R gives time and years that it would take to triple. How long would it take to triple an investment of $500 at 5% annual interest? And here's a formula for tripling. Okay. So all I need to do is put a number in for r, right? What number are we going to put in there? 0.05? Okay. So we've got the oh, that's right, we got this fraction key. I love that fraction key. The natural log of 3, close your parenthesis, and the natural log of 1 plus 0.05. So how long would it take to triple an investment of $500? It would take 22.5 years. Okay. All right. Has absolutely nothing to do with the value you put in. It has everything to do with the interest rate. Okay. All right. So letter B, it says what interest rate is needed in order for the investment to triple in 15 years? So we're solving the equation. We're solving the equation that 15 is equal to the natural log of 3 over the natural log of 1 plus r. So we need to solve that equation for r. And when you do that, you will get approximately 7.6%. So type it in and check that, see if it's correct.